Well, that's paradoxical. That was a mixed message. Can you hear? Wait, can you? Hello.
Yeah,
Yeah.
you.
Thank you. Okay, thank you. Awesome, great. And hi, excellent. Hi, hello. Thank you. You, thank you. Good afternoon, indeed. Awesome. Oh wait, but you don't see, or at least I don't see you seeing me. Or I don't see. Okay, okay. Um, Hi, right. Okay. Hopefully, some of you have been getting back some of the points that I want to continue to be giving you, promising you. You all have been very flexible and um, adaptable and driven. I'm totally psyched that you continued the conversation even after I left. I don't know for how long you did, but I think it's great that you did. And I guess we're going to hear. We're going to keep doing what we're doing. Well, what we're going to do right now is, for starters, I'm saying, however we're examining you, however this exam is going to happen, or however we're all going to get, first and foremost, like the number one first problem that will definitely be on the exam is the very first problem that you all want it to be. In other words, I'm hoping, and we're going to find out in a minute now, I'm hoping that if nothing else was able to happen, like last Tuesday when like I was barely there, if nothing else happened, I'm sort of hoping that, or can happen now, I'm hoping that the group gravitated towards, I'm hoping that there's at least one problem in that packet that you guys sort of feel like, at least with help, you could tackle and manage. And so what I'm here to say is, like, you guys tell me the problem, like however maybe you've already discussed it or maybe not, but whether through the chat or through voice, you tell me as a group what's the first problem you would like to be tested on, like that you think you can handle of those that are in the practicing. And then I'm going to assume that that still doesn't mean you think you're perfect with it. I'm going to decide, I'm going to think, okay, that's the first problem that's definitely on the exam. So let's discuss it now. In other words, and then I'll take so whether you, and then you'll either, if you want to take more time on it before you ask me questions or not, that's up to you. But basically, you're going to tell me now which problem of those 5 or 6, which one you feel most comfortable trying to tackle, and we will tackle it together now. That's what I'm saying. And I'm talking about of the practice document. So, and I can also walk away for 5 minutes if you want to discuss it amongst yourselves. But B and C. Okay, that's concrete. B and C. Let me look. Of course, I'm saying all this. That B and C. B and C of 1 or B and C. Wait, okay, I'm totally. And yeah, and by the way, that's exactly how I'm planning on just doing whatever anybody says. Like if one person says something, I'm going to do it. Like Rain. Now Robert's saying something cool. So the more you guys respond, the more I'll wait until you come. You can disagree with each other, and I won't do everything. But as long as if there's only 2 voices, I'm going to do what the 2 voices say, kind of thing. Like we're kind of always doing. So wait. So I'm looking now. I'm opening the document. I'm looking for both what Rain said and Robert. And again, other people should or could chime in. They should either be like, yeah, let's do what Robert and Rain are saying. Or if you think they're about to take control of the class in a way that you would not benefit, someone else. But wait, why can I not see what? Okay, there's a document. In fact, I'm going to share the screen in a minute of the document if that helps. But I'm thinking, okay, Rain is saying, oh, B and C. I'm thinking Rain means B and C of problem 1, which is fine. And then I'm assuming that Robert means also number 1. In other words, until I hear otherwise, I'm going to assume I'm going to interpret Robert and Rain to be asking ultimately for the same thing, the entire package of problem 1. And I'm totally willing to do an entire problem. I don't know if I can do 6, but I can certainly do 1. So as it stands now, if I'm interpreting Rain and Robert correctly, besides thanking them for their input, I'm about to dive into problem number 1. And I'm thinking that means that if I help people with it, that they already have, that help will be helpful. It won't just be a lost cause. But so stop me, anybody else, or either they should confirm that I'm interpreting them correctly, or other people should be like, wait, no, I was actually really into problem 3. But I'm perfectly happy to do. I want to do it this way. So I will at least share.
Professor?
Oh, yes.
Actually, I was saying like B and C should be on like the exam, but I would like to go over A of 1, like the differential equations part, question
Sure.
A.
Oh, okay. Well, that's still perfect. So in other words, if I'm understanding you correctly, okay, and thank you for correcting. If I'm understanding you correctly, you're saying you think you could handle it if B and C were on the exam, that would be cool, but you would need help or want help to see with A. If that's what you're saying, Okay, that's great because definitely to everybody, what I'm saying, like, since all of those are part of number one, right? I'm totally, if, so I'm saying this to everybody, if Rain is directing my attention to certain parts of one, I totally will go over all the parts right now without any problem. And then I would totally be saying, yeah, then we're going to put problem one on the exam. Like, so it doesn't, she doesn't need, I guess what I'm trying to say to everybody, if I'm understanding, I'm perfectly happy to do number one now, A, B, C, etc. And that would mean still that I would put it on the exam. Like I won't not do it just because I helped. Oh, and okay, and Durkel is chiming in. Okay, right. So yeah, hopefully, in other words, hopefully what you guys think you can manage and what I actually help with now and what's on the exam. I don't mean for you to be choosing among those. I'm looking for the top choice. So far, it's looking to me like top choice is problem one. Like if that's okay, and that's I think is what Durkel's saying. Okay, cool. Because yeah, I mean, okay, cool. Part of it, and if I'm still looking at the chat when people are still coming in, so I'm stalling a little bit just to make sure I'm understanding. But so Rain, I mean, is that right? If I go over problem, if I sort of promise to do all of problem one this year, does that cover like all of what you're saying, Rain? Just to make sure I understand. If I mean, and then say it's on the exam. If I go over it and promise, like, yeah, what I went over is a big part of the exam, that would satisfy what you're saying. Yes or no?
Yeah.
Okay.
I mean, I didn't get a chance to look through the whole practice midterm, but that sounds good.
Oh, okay, that's fair. Oh, yeah, okay, I see, I hear you. Okay, right, all right. So far, I'm still going with that to everybody, but I'm also hearing what Ray's just saying. Like, yeah, I'm not trying to. I know this is so unusual to everybody. It might even be freaking people out how I keep, so to speak, adjusting or something. Like, I'm not. It's not meant to be a trick or a trap. So even when I'm asking you guys to decide, like, what's your top number one preference problem, don't even think of it. It's not one of these like, so aha, now you all pick number one and now you're committed to that. So secretly, it would have been much better if you'd picked five because that would have been a cruise. But now I'm taking it away from you. Ha, like I'm not going to do that. Or certainly I'm not going to intentionally do that. I'm basically trying to have all you guys help me construct what you think is the sort of most fair and manageable exam experience for you in advance so that we can position ourselves all to actually get an A on legitimately hard physics. Because by the way, you know, no matter how you look at it, any of you guys, you look at this stuff in the exam, it's real physics. I don't think that can be denied. And like, so if anybody at the end can honestly say to themselves, they can do this stuff, then they're doing real physics, right? But you know, we're not going to do the infinite expanse of all of physics. So I'm trying to help us together choose it. So yeah, so this is a long way of saying, even by doing number one right now, I'm not saying to you guys, you just like shot your chances of anything else easy being on the test or something. It's nothing like that. We're just trying to shape this together. Okay. So far, according to the chat, anyway, it's looking like number one would be a good thing. Okay, well, as in differential equations. All right. So if nothing else, in a moment, just so I can get rolling, I'm going to start rolling on problem number one. Like I'll do it in order A, B, and C. I'll say again as I'm going that you can assume that if you really get this, like please try to get whatever I'm saying and ask me whatever questions and pin me down because like a very, very similar version of it will be your exam thing. Like, you know, it won't be the whole exam, maybe not, but you know, you can assume. And of course, I'll change certain details just to make it like not just so that I don't just have everybody, excuse me, so it's not just an experience where everybody hands over a check to Chegg and Chegg takes the test for us. And like, so I'll change minor things. But anyway, all right. But until or unless I hear otherwise, I'm doing problem one. If anybody does want to tell me in the middle to abandon ship and do something else because then they can do that too. I'm just looking at chat to make sure. Okay, so I'm thinking number one. Okay. Hold on, I'm going to do it on the screen. Sorry, bear with me for a minute. And what I'll, oh yeah, I see why this is a good, yeah, okay. 1 second. Okay, tell me if you can see the screen. I'm doing. And sorry, can I just get a vocal? I'm looking while I'm, are you seeing the screen, you guys? Because I'm looking, my windows are all, can you
Yep.
see? Yeah, okay.
Yes.
All right.
Yes.
All right, thank you. And this is what I'm, okay, great, okay. Okay. Oh yeah, I could see, this is totally worth doing. Oops, excuse me. This is, yeah, okay. I remember what it feels like to have to face a physics exam with an opening problem like this. Like, so I'll just say quickly, like, I hope ultimately you can see this is, we've been doing this a million times. Like we're being given a function here, a function of one variable, like one dependent variable, one independent, and we're just at first just being asked to take derivatives. So in some sense, of course, this is just straight up practice of like power rule or something in calculus or chain rule. And where this is going. Like we're going to take two derivatives and then see about the differential equation. But I also want to quickly admit or recognize to everybody, like, of course, the actual function here looks bizarre. Oh, I mean, there's like all these crazy letters in the TU, but you have like the whole point of that is if you stare at them hard enough, or if you've gotten used to this whole thing enough, you know that what's special is variables versus constants, right? Like it doesn't matter if it's y or x or u or t. What matters is where are variables and where are constants. And so, partly you just want to not be befuddled by how weird the constants look. You just have to understand that they're constants. But also just know in the back of your mind, it's not a coincidence that they're not put there just to jam you up. It's actually like the next equation that's coming in physics. Like it actually is a real thing, and it's trying to show you like that the difference between form and substance, like just know the form. But anyway, all right, I'm going to do it. So we take the derivative. So I'm going to take the derivative knowing that the variable is t, everything else is a constant. So, okay, so, oops, but then chain rule, so. Right, unless I'm crazy, right? So this is, yeah, like all that business before the t is all a constant. So it comes out from chain rule, but we get negative sign because it's a trigonometric. So that's, okay, so that's number one. Stop me if, and I'm not looking at, I can't look at the chat. Well, I can, but I'm not while I'm doing this. But then we take another derivative, okay. All right, and this all looks like this might well all look like gobbledygook, but I am just following the instructions of the problem. I'm sorry. Oh, and then, oh yes, it does ask, okay. And so the next question is the important thing. I'm just looking at the chat. Okay, let me just look in the chat, sorry. Oh, yes, we can, okay, cool, okay. So now I have this gobbledygook, but now comes the important question, which is, right, is this thing a harmonic oscillator or not? Is this system being described here and what that means, and the real, what does that mean? That means, like, that's a very specific question. That's a mathematical question. It means, can I capture the dependent variable here and the independent variable in that particular differential equation, which is the harmonic oscillator differential equation? And it's just a matter of, of knowing which the variables are. Like here, the variables, I believe, are lowercase r and t. Yeah, the variables are r and t. So in order for this to be a harmonic oscillator, the following would have to be true. Like the question is whether the second time derivative of r is directly proportional to r itself with a negative sign. Like that's the question. I haven't answered it yet, but that's what I need to know in order to answer whether this thing is a simple harmonic oscillator or not. And by omega squared, and this is where it does get a little bit like omega squared is just a fancy name for a constant, any constant. Like we write it as omega squared for a reason, but that reason has to do with convenience. We could have written it as omega cubed or omega itself. The point is just whether there's a constant there whether we can find this relationship between the second derivative and the thing itself or not. And so now I turn back and look, like, because we've just found it. Apparently, what we're saying is, I look back at what my second derivative is, and I have, okay, I'm going to forget, but what we have figured out already is oh, come on. We said on the last page that the second time derivative of r is negative r, blah, 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 stuff. What does all that stuff mean? Well, remember what we had said. I mean, multiplication is commutative. I'm going to go on the next page in a second. But, like, remember, R itself is this piece here. So evidently, in other words, I guess what I'm saying is, I don't know. I'll go back to that last page in a second, if that would be helpful. But I'm saying this. I don't think I'm getting this back. What am I doing? So what I'm, okay, so, well, I was trying the experiment of writing without talking. So what, so my answer is, this is a harmonic oscillator. This is, and this is not a trivial problem. Like, this is the problem that we studied for a million years, like at the beginning of the course. Like, I think it's totally, like, it's not out of nowhere, blah, 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 but it is not a joke, right? It's not easy. So let me explain, maybe if helpful, what I just did. I mean, what I was trying to show back here, starting from, I guess, this page, like for something to be, for some variable to harmonically oscillate, for any conceivable dependent variable, any measurement that you could make, that you could track in time, for any variable in the world to harmonically oscillate, it means that the second time derivative of that variable is directly proportional to the variable itself. Like, that's literally what harmonic oscillation means. In other words, this diff-EQ, this differential equation. So we're trying to prove that this R, the given R case that we were given, this cosine gobbledygook thing, we're trying to figure out that whether or not it was true of that function that its second time derivative is indeed directly proportional. And what I'm ultimately trying to show here, and I don't know if it's overkill or underkill, but what I'm ultimately trying to show here is, oh yes, if you differentiate r twice, what you do get is negative sign times omega squared times r itself. Like, yes, you do, as long as you recognize that omega squared is just a fancy name for any constant. And what we have here next to the r, is indeed any constant, a constant that happens to be called u squared over capital R cubed. Like, that all just makes it all intimidating and maybe seem almost unfairly like cumbersome, but all of that just means constant. And omega squared, in fact, all of that means constant squared, if you like. And omega squared just means some constant squared. So as long as, oh, and yeah, this is hard to read. As long as by omega squared, we mean the same thing as u squared over r cubed, then yes, this is a harmonic oscillator. And just to be like, why would we write it all like as u and r? Like, why would we ever do that? Because what we're really secretly saying here too is any oscillator in the world is something that mathematically acts like a mass on a spring. But every oscillator in the world actually has different properties. Like, one is actually a mass on a spring, another is a pendulum bob on a string, another is an atom on atomic bonds that are springy, another is like, so all the springy things in the world all have actually different like omegas built from different parameters. And the one that we happen to be looking at here, just if you want to know, happens to be like a gravitational tunnel that's oscillating back and forth, you'll see. But so the point is, that's where the constants describe the actual material parameters. But what we're proving here is, anyway, I'm going to move on. I know that doesn't help with the exam. The answer is yes, this is a harmonic, and I'll just keep going unless there's any, because I don't think there's anything in the chat. Okay, I'm just going to keep going. Sorry. So the answer is yes, this is totally a simple harmonic oscillator because D2R, because of this, because what I just erased without meaning to. Undo. See, that's what the older generation doesn't understand. It's all about undo. But you see, what the next generation doesn't understand is it's all about redo. No, I have no idea what that means. It's all about the D2R over dt squared equals negative omega squared times r. In this case, yes, as long as omega squared equals u squared over r cubed. That's the answer to that one. All right. But it goes on, the problem, I know. Now, B. All right, switch gears. I guess that means change pages. So we're now on B. So, okay, and why is it saying switch gears? Like, this is definitely still the same topic, but we're now introducing a whole, we're now introducing a whole other function. Like, we're switching gears because we're picturing a different potential mass on spring system. And this time we're given, okay, so it's like a Z and T now, okay? The given here, and so, and these are intentionally, they're not tricks. They're systems that look like potentially they could be oscillators because they are functions where if you take two derivatives, you do get something that seems like the function, like sines and cosines do that, but we don't know if the details are right. We're sort of really asking ourselves, are the details actually lined up to make the negative sign and everything work out to be like Hooke's law? So, okay, that's our function. Given that, the question is, does it satisfy, or is it true that this? And again, we have to recognize that omega just shorthand for any constant at all. Well, here it's that constant. Okay, well, so how do we know? We're going to just take derivatives. Like, now we're just going to do the procedure that we just practiced in the first problem. The assumption is now we know how to do the whole thing. Sorry. I'm just going to change colors for no good reason. So D, Z, G, T. This is just chain rule and trigonometric. So it's omega b cosine omega t, because the derivative of sine is simply cosine, like there's no negative sign that comes in there. But now we take another derivative. So the omega comes out again, so we get omega squared b, but now we do pull a negative sign because the derivative of cosine is negative sine. Okay, so this is the second derivative. So now I go to the next page. I apologize, and I can go back. So far we have, the assumption was that Z equals B. this was a given, and we so far have established that this is true. And so the question is, does and the answer is absolutely yes. The answer to the question is yes, because this right here is Z. So yes, this when you take the second time derivative of Z, you totally 100% and directly, literally get negative sign times omega squared times Z itself. Like in here, it's a nice clean thing where the omega was already packed into Z. So like yes is the answer there. Hold on, let me just look at the. I get so confused. I'm so old. I mean, I'm not. I mean, I am, but I'm okay. Chat. Okay, but I'm just gonna keep. I almost feel weird, but I'm just gonna keep plugging until or unless. Sorry. Okay, so I'm going to go on. That's that. I think I just showed why. So yes, the answer is yes because of what I just because Z, because it does. Okay, now this is getting almost like, I guess, a little bit redundant and annoying. Yeah. Oh, I can see why you want problem. Yeah, this does get a little bit. Never really gets to the punchline, does it? But it's an exam. It's what it is. So where are we? So C1. Okay. Oops. But stop me if I'm in the wrong place. So we now have is. And I think we practiced this in class. Oh, but yes. Now, what this is seems like more of the same. I mean, and it is more of the same. But what actually it's trying to get at now is it's saying if it's really been now properly drilled into our heads that anytime we see a d2 blah, equals negative omega squared blah, like any variable about which that thing can be said, that differential equation that we keep harping on, our whole point is that anything in the world that can be described that way is a harmonic oscillator. And that covers a lot of ground. And that means that we've established that anything that can be just anything that's a harmonic oscillator can be described with a cosine function. And so that covers a lot of ground. What we're actually asking here now is, are there other ways to describe oscillators besides cosine functions, like, for example, exponential functions? Like I think we talked about this in class, but there's a reason to worry about this because with exponentials, you get, and when you take derivatives, you get back to the function itself. They're self-referential, they're feedback functions, just like cosine and sine. So there's good reason to, we're now asking, can we satisfy a harmonic oscillator any other mathematical way? I think we did this in class, but either way, we're just going to follow the rules and take derivatives. So I'm going to the next page. Again, we're saying, we're saying x equals e. I don't think we put a negative sign. Oh, we did, sorry. E to the negative omega t. So first of all, what is dx dt? Well, this is chain rule and the definition of the exponential, i.e. what comes out is the negative omega. And then we still get, that's the first derivative. The second derivative, oh, no, I'm just kidding. I'm so kidding. Okay. Isn't that funny? Okay. That's the second derivative. So, okay, that's the second derivative. Now the question was, does this function satisfy the original differential equation for simple harmonic oscillation, which is this? And the answer is no, right? The answer is no, 100% because there's a negative sign missing or a positive sign not missing. I mean, It's like, it's very darn close. It's exactly similar, except it's wrong in a super important, crucial way, that there's no negative sign. In other words, so I'm just gonna write this, and I do see there's something in the chat. Pardon, sorry, but I just want to write this clearly, and the answer is no. Like literally no. What's the reason? Because -1 does not equal +1. Like they are different. But hold on, let me look in the chat and see if it's clear enough. Oh, sorry, I totally missed. I think that, sorry, Sarah, thank you. That must have been a million years ago that you put it in, and that was 4 minutes ago. That was 240 seconds ago. That was 240,000 milliseconds ago. I apologize. I totally missed. But yes, you're correct. That one was true because B sine omega t is equal to Z, and that's also 50,000 millipoints. And I'm only not being sarcastic. I mean, I'm not being sarcastic. I am, but I'm not mocking you. Okay. So yes, this one's no. And this is important again because like this is a subtle difference. It means something has to be corrected. Exponentials are almost cosinusoidals, but they're not, and they really aren't because they exponentially go on and on forever, like in one direction, whereas cosines go back and forth. All right, so that's no. Oh yeah, but so the problem does go on. I actually do. I have to admit, I find this actually very mathematically interesting, and I think it does all relate to the virus too. And if there's time, I'll try to show you guys. But I can see why this is like hideously painful if you're not, say, me. But okay, but going on, but it is all actually saying something. If I go to the next case in the exam process, so I'm on page 5. Page 5. It now says now assume. And I think I do remember, but yes, please stop me if any of this. Assume literally this. Now, I do love this, okay, because this opens up a whole world called complex numbers, or you could go imaginary numbers, hoo-dee-ha, and it does get fascinating if you want it to, but none of it has to open up at all, and nothing has to be fascinating. Like all we're literally saying now is whatever the square root of -1 is, like whatever you think of as square rooting, and whatever you think of -1, well, like do that first thing to that second thing in your mind. Like if you know what it means to square root 7, all right, instead of that, square root -1, and whatever that is. And if you don't, if you're like, I can't even picture that, whatever it is that you can't picture, put in a black box and put a seal around it and call it I. Like literally, that's all we're saying. Like I is now the letter that stands for that concept. Okay, but whatever that concept is, it is a numerical concept. It's a number, and it's a constant number. Like maybe I don't fully even understand it. And maybe I don't, honestly, like the square root of -1. I don't know if I fully understand it. I don't. And maybe you understand it slightly less than I do, maybe. But whatever it is, it's a freaking number, and it's a number that's not going to change. So any calculus thing that we're going to do now, we're going to apply calculus to this thing as though it's just another number that we hadn't thought about before. I.e., it's a constant, right? It's going to be a constant, not a variable. I mean, just, and it's just going to equal that. So if you square it, the whole thing will equal -1. Yeah, it will equal -1. All right. So given all that, then given, or let, I guess we said, let, now try this function. And it is really weird that this works. And then first we're asked for, I know my color choices, random at best and hideous at best. But the first derivative, okay, chain rule, and that I thing there is just, it's like the letter A or something. I mean, it's going to come out, it's a constant, so it's going to be part of the chain rule. So that's chain. And this all assumes, I'm sorry, one thing I'm being glib about. I am doing chain rule every time, but I am also assuming, just to be as clear, like I'm assuming if y equals e to the x, like just the most general thing I could say, if you have some function e to the blah, then I am assuming that for all time, the derivative of that function is literally is the same thing. Like, in fact, that's almost the definition of e to the x, is the function, which is its own derivative directly. Like I'm not saying I've proven that in this class. I could. That is a mathematical thing, which is super cool. But I'm not saying we've proven in this class. I am saying we are assuming it or relying on it from the mathematicians. But then I'm applying chain rule. It's okay. So I don't know if that helps anybody or if that clarifies anything, but given that the first derivative is, and that is, but that is a fascinating thing. It's all about what feedback really means. But so that's dx or dt. So then if I take the second derivative, then the negative comes out again. So now I have, so negative times negative is a positive, but an I comes out again. So I have I squared. The omega comes out again. So I have omega squared. And then I have the gobbledygook, which is not gobbledygook, but is. But now, and you may or may not remember this, or we said this before, but see if I can fit on. Like, that is the answer, strictly speaking, but we can really simplify that a lot. We can really make a lot more sense out of that answer. Because well, my handwriting is also hideous. That's supposed to say, it says positive I squared times omega squared. Okay, I squared. What is I squared? Well, I is the square root of -1. I don't know what that is any more than you, but I know if it's the square root of -1, it means it's the number such that when I square it, I get -1. Like, I squared is by definition -1. So that whole thing turns into a -1, which means I really have this. Okay. And the question was, was this thing a harmonic oscillator? And the answer, I think you can see, I hope you can see, the answer is totally yes. Yes, yes. The answer is yes, it is. This is a harmonic oscillator, which is a very strange, what we're really saying is, when you picture harmonic oscillators, we're saying they're all described by this differential equation, which is like a feedback description. But when you picture the oscillator itself, whether it's a mass on a spring or a temperature reading on a gauge, like whatever it is, you can picture it going back and forth, back and forth, back and forth, like a mass on a spring, but like a cosine, right? Like, cosines are what you picture as the actual action of an oscillator. We're now saying that cosine you could also picture as an exponential, which means something that you would normally imagine as like monotonically concaving, forever in one direction, like getting steeper and steeper and steeper, or less and less and less steep, but like always doing the same thing. Somehow that you can picture that when you're trying to picture an oscillator, as long as it's an exponential to a complex power. I mean, in other words, once you put together exponentials with imaginary numbers, you get oscillatory behavior. That's a very weird, separate thing in math. But it's true. Anyway, it's true. So the answer is yes. And you don't have to worry about all that if you don't want to. The answer is yes. Wait, let me look in the chat. Sorry. Oh, maybe I made a mistake. I'm seeing the chat. Sorry. Wait, isn't the I squared? Hold on. Sorry. Isn't the I squared supposed to be front? Yes, it is. Wait, isn't the I squared supposed to be in front? Yes, the I squared is supposed to be in front. It is. You're right. So what I'm saying, though, and I'm totally glad that Raina stopped me on this, whether it turns out that like I made a mistake or not, yes, it's supposed to be out in front. But I think what I'm saying is the big breakthrough. I'm saying that I squared equals, by definition, must equal -1. If I is by definition the square root of -1, then I squared has to, oh, you're right. I'm saying yes, that's what Hyun-Jung Kim is saying is what I'm trying to say. I don't know if that clear. So I changed that positive I squared to just a negative sign, which like abbreviating for -1. Does that make sense? I'll pause for a second. Oh, okay, cool. Thank you. But cool. That is that problem. Now, again, as far as I'm concerned, and really, this is not meant to be a trick contract or something, but like, I want to say, because I feel like we've now talked about it and you guys like, I'm going to say, okay, there's part of our exam will be a problem like that, like very, very much like that. So please do like keep staring at it and make sure if there's another question about it, like now, I would love to take it. And And even if you remember, even if you feel like you're now just figuring it out for the first time, good. That's the point of why we're all doing this. If you feel like you figured it out a long time ago and you're getting bored and you want something new, direct my attention to another problem, obviously, in a minute. But the point I'm really trying to make with all this stuff is that it is never too late. Let's just get it. And there can be not too much. Success doesn't have to be competitive. We can actually all help each other get all of this. And again, remember, this is hard enough conditions, this whole Zoom thing and the virus and everything, and me changing the ground every 5 minutes. It's hard enough conditions that some people will fail, no matter how much all of our good intentions are. So as long as we're not those people, we will get A's and B. It'll be hard to be in the middle ground. So why am I defending that? Because what I'm saying now, what I'm saying now is that problem now is on the exam, and you can still ask about it if you think of something to ask about it. But I'm going to hope and assume that it's sort of a clear, tidy, clear package now. I'd like to do, it's 12:50, we have a half hour. I'd like to do one more, but I'd like to do one that's your choice again. I know I will certainly say to everybody, because again, this whole practice exam, it's great and everything, but it's way too big. The problem number 3 is the one I would worry about last if I were all of you. Problem 3, in a way, if you can get through it all, you'll learn a lot and you'll really be able to do everything. But it's kind of a nightmare to read, problem 3. So I would save that it would be the least likely thing that I would want to put on. If you're not interested, I'm not interested. But any other problem that anybody sees, if you direct my attention next, I'll do next. And and make the real thing. In this class, we have not talked about cross products yet, correct? Can I get it? Yeah, we are not going to put no. Okay. We are not going to put 3 on the exam. I can promise you that right now. Because you just said that clearly, I'll say it clearly. That's fine. And we will put number 1 on the exam. I would love, let me see if I would, you know what? I can even, oh, yeah. Honestly, I think number 2, I can definitely agree to say no number 3, and I mean it. Wait, what did I just say? Yeah, definitely no number 3. So what I want to say is I think number 2 is actually perfect. I'm also going to eliminate another one in a minute, but I think number 2 maybe looks horrendous or something, but it's totally fair, and it's based on the lab and everything too. So you know what I want to say? Number 2, right now, why don't you guys we still have a half hour today. Take 10 minutes or 5 to 10 minutes to try your best at number 2 right now, or to try to get the lay of the land of number 2. Try to skip around if you have to, but try to get to the heart of number 2 on your own for 10 minutes, and then I will go over it for the remaining 20, and we'll take things from there again. We're going to take this thing when we're ready to take this thing, okay? It's not going to be a sneak attack. But I like this, that I feel like we're more on all the same team, just trying to nail this together. So take 10 minutes to work on problem number 2 is what I'm advising everybody or requesting everybody on problem number 2. And I'm here to answer questions, but then I will go over it. So I'm trying to talk as little as possible, but uh, um, just to be clear, so on the FBD, which is important, like the FBD is really actually how you know that this thing is a harmonic oscillator. That's sort of what you showed in lab, blah, blah, blah. But with FBD, it's only asking for an FBD. It's super important and it's super simple, but it's only asking for an FBD. That means all you have to do is provide the actual pure FBD, free body diagram, which is to say this right here. And it's really simple, but it's really important to know how simple it is because that's the whole thing of FBD. But anyway, it would be correct if you're understanding, like if you have a pendulum drawn the way I did. I mean, of course, your pendulum could have been drawn on the left side and then your whole diagram should be on the left side. But if your pendulum looks like mine does in the picture, then your free body diagram should look like mine. There should only be two forces. One is the tension from the string, angled at whatever way the string is angled, pointing toward the fulcrum. And then the other one is gravity, mg, pointing straight down. Like those should be the only two forces. They should not be aligned with each other, right? I mean, they should be at some angle. And that's all that needs to happen in the free body diagram. Now, but this always happens on exams. If you want to include components, because in fact, components actually do make it easier to do math and stuff, great. But do it correctly. Because I think secretly a lot of people don't actually understand the difference between components and forces and stuff like that. And you don't want to just open yourself up to that jam if you don't have to. But if you want to do components, do it because you actually understand the components and you find it easier to picture or memorize or whatever. So a component diagram would look, for example, like this one here, like that's correct, dividing mg into components, but then don't divide t up. Or you could maybe do something like this. You could do something like this. Like you could divide t up and not divide mg. And you can but then you have to be super careful because the upward one will be t cosine. I don't even want to write it. And the sideways one would be t sine. Like that would be technically a correct diagram, but then you wouldn't be able to do F net equals MA with it for reasons that are not worth going into right now. And it would be a bizarre, and you'd have to know that sine is this way and cosine's that way. So if you're going to do components, I highly recommend doing like that. But I will say this is something I'm very picky about, especially with a take-home test or whatever. Like, don't have mg and mg's components in the diagram. And then if I take off points, I mean, I'm already having like a fantasy fight with that. That never happened. But like, it does often happen that I'll get picky with something like this because I think it's very conceptual. And someone will say, what? No, I was just including the components, like the components because I saw it on the internet or whatever. You can include components, but then it's a component diagram. If you include components in the diagram along with the original force, if you have mg and mg cosine theta and mg sine, even if cosine and sine are correct, which are actually very hard to get correct in this case, but even if they're there along with mg, then you've double counted mg. Then you're literally putting mg twice. And that's where I would be picky. So anyway, the free body diagram is just the free body diagram. If you want to do the components, it looks like this. Okay. Then omega, I'll go back to not talking, just something in the chat. But then the next question was, what's omega? Like, we're trying to show here that everything we know about the math of a harmonic oscillator really applies to, like, we're trying to say we now can understand all oscillators in the world are all mathematically like masses on springs. But even if when they don't look like it, and even we don't see a spring or we can still deal mathematically. That's what's happening here with this pendulum we're analyzing. Okay, so we are now saying if it obeys that harmonic oscillator differential equation, then the constant of that equation is omega squared. We call it omega squared because whatever it is the square of the angular frequency of the oscillator. Like, so that's where I got, so going back, that's where I got, excuse me. Well, that's where I got this second answer. So omega is literally the square root, like, right? Because we're saying this is our harmonic oscillator. It could be any variable. In this case, the variable itself was theta. A little confusing, but that's because it's a pendulum. It's like swinging in an arc. So we're literally saying this, but the omega here is pi over 4, like the square root. Okay, so pi over 4. We get that to 3 significant digits because it asked for that. So that's part 2. Go on to the next page. Pardon me. And definitely stop me. Oh, sorry. Okay, and so the next, I'm looking at the next page. Oh, all right, so now it asks, I guess I should turn it to, well, you're welcome to answer, any of you. If you already got an answer, and if you either want to speed me up or get points or whatever, I'm cranking through just because I think it's what people want. But if you guys already got an answer to, sorry, we're out to 3. Yeah, if you already got an answer, feel free to shout it out or privately chat it or publicly chat it. But if not, I'm going on and I'm saying, well, this is what I think. I think there's so many different ways to look at this, but I think this, like angular frequency is radians per second, right? Angular frequency is a measurement of cycles per second, only it's measuring in radians rather than cycles. And there's 2 pi radians per cycle. In other words, omega is 2 pi over the period. Like there's a million different ways you can memorize all these relationships, but that's one way that I like. So, and it's asking me for the period, and I already have the omega. So I'm doing this. And we're trying it, because we're being physicists here, we're trying to get actual numbers with significant digits. Don't be scared when we say significant digits in exam. What we're saying is give us actual numbers. Don't leave it as pi. I just lost, yeah. So we're saying, and I forgot already what omega is. Sorry, omega is a 0.75. And everybody's answers here will slightly numerically differ. That is totally fine and not the point. So, but I'm getting like this. Okay, so the period is approximately 8 seconds. Sorry. Yeah, sorry. That is correct, but that's not the answer yet. The period, okay, so the period is approximately 8 seconds. That means the amount of time for one cycle is approximately 8 seconds, just based on the way the differential equation was written. But what's being asked here, exam obnoxiousness, is it's actually trying to make sure that I understand the English. So it's asking me for the amount of time for 3 full round trip swings, right? So what we want for the answer to this question is 3t. So 3t approximately equals 24.0 seconds. So that's the answer, like approximately 24 seconds. That's the answer to Roman numeral 3. Please feel free to chat me. Don't forget, oh, there is a chat. Don't forget to chat or subscribe. Okay. Oh, yes, awesome. Sorry, and I missed it again. Sarah, yes, totally. Oh, it's like it's like me sending Christmas cards like after New Year's. Like it's just a day late, dollar short. Sorry. Yes, Sarah, totally. Thank you. And that's like points. Hopefully you guys saw some of the points that came back in this morning and more are coming. But all right, that's that one. That's 3. Then 4. Measured in radians. Oh, this almost gets interesting now. Oh, this is like, this is certainly hard. This is not easy, this one now. Okay. Oh, it's also incoherent. I'm sorry. I'm glad we're going over this. This question is, it's not an easy question, but there's also a mess. I'm sorry, in this draft. Let me see if I can't annotate yours. I'll try to re-upload a fixed version, but if you're all hearing me right now, yes, question 4 has a major typo that's like 2 lines long. The question is just, what is the particle's approximate speed at? That's all I need to ask. All the garbage, I don't know. Let me see if I can, 1 second. Hang on. I apologize. I will try to remember this and upload it. What I'm about to do, the annotation I'm about to do, or yeah. Like all this, can you see on your, I think you can, yeah. Everything that I'm putting a red arrow through, just cross out on your end, please. All the way through. That's just total garbage error. The question should say, what is the particle's approximate speed? Okay, can I just get did anybody just catch that? I mean, I will try to re-upload the fix. Could anybody just say yes or something if you just caught that I just made it? Okay, thank you very much, Sarah. I appreciate it. That's 50 million bazillion points. Okay, thank you. So the question still, it's a little bit easier if you know that it's not total garbage, but it's still kind of a hard question. We want the particle's approximate speed at t equals 1.33 seconds. Okay, it's actually a good question. It brings a lot together, and it may be the last one we do. It will be the last one we do today. I'm going to switch to the screen. Sorry. Okay, I can't. Is it 4 that we're about to do? Sorry. Yeah. Okay, we want the speed. The key, we want the speed at a particular time. So we want speed as a function of time. Right, put another way, we want velocity. We want the magnitude of velocity as a function of time. Okay, well, where in the heck would we get that? Well, velocity is the first derivative of position as a function of time, right? I mean, that's maybe a big mouth, but that's the key. In other words, so what is x as a function of time? Well, we know this is a harmonic. We know. Now remember, so okay, so we know that this is a harmonic oscillator, and we know the dependent variable is theta. Now it's a little it's about to be a little bit confusing maybe that it's theta, but remember the dependent variable could be anything. It could be called z, it could be called q. In the last problem it was called lowercase r. The point is that the dependent variable here harmonically oscillates. Therefore, we know like I guess to be as clear as possible. And I'm looking at the time. This is definitely the last thing we're going to do, but I do want to do it. Remember, like the key to all of this, and it always looks deceptively simpler than it is, or more complicated than it is. But we know that for any variable, call it z, if any variable does this business, then we know that the variable follows this. Right, that's what we're really over and over saying here. Like if the thing harmonically oscillates, it can be described by a cosine. Whatever it is, whatever the variable is. If it's z, then z. Okay, now in our case, the variable is theta. So that may throw us, it may look funny that we're about to put that in funny places with the cosine, but our variable is theta. So here, right here, I'm going to even go on the next page. Here, what we have is the variable is theta, and I am watching the time. We will stop. Right, we have this. So what we know is that here, we know that theta equals, we know that because it's a harmonic oscillator. Okay, now that's theta. Well, what we want x as a function of t. We want x because we're looking for dx dt. We have theta. What's the relationship between theta and x? I'm just going to say it because we're running out of time. Like in other words, we have angular position as a function of time. We want regular old translational, like linear position, like x coordinate as a function of time. What's the relationship? Well, the relationship is theta by definition always equals arc length divided by radius. In other words, x equals theta times r. So what I'm saying, and I'm just about done here, this is a little bit of a leap. This is the hardest part of the whole problem, maybe, to make this connection. But if we know that theta equals theta prime cosine omega t. Therefore, theta times r equals r, like multiply both sides by r. And that's what x is. X is this function of t. Therefore, and this is the last line, and we'll stop here and don't do anything. I mean, we're just going to keep going like this until we can all don't take an exam tomorrow. Just keep up with what's going on, and we'll meet on Tuesday and keep doing this. But let me finish this problem. Dx, unless everybody objects, but dx dt, it's all about course correction. Dx dt equals, right, so chain rule. And so then you plug in. For r, we know, and I won't solve, but I'll just put in the numbers. We know that r, I forget, r, sorry, you know, wait, R, yeah. 8. Whatever we got is. I will stop in 1 second. I'm just looking for that number that I lost. What is the number at 0.785? Okay, I'm not gonna, because I just ran out of space on the thing and because it's 1:30, I'm not gonna plug in the numbers right now. You can in your calculator, but that is how to get the answer to that one. And what is that? That's, yeah, that's definitely a good place to stop right there. I know I'm being weird, but I'd like to just hold everything at that thought. Okay, are we? I'm going to say goodbye if anybody else says goodbye. Oh, that's fair. Wait, of the exact answer of this one? Wait, is it? Yes, I can. That's totally fair. I didn't want to hold anybody, but I could totally tell the exact answer. But are we talking about the one that the exact answer of this, what I just did, or of I? Wait. Young. I can definitely tell you the exact answer, but of which one? Oh, number one. I think I know what you mean. The exact number one. Oh, the FPD. Okay. Yeah. The exact answer of the FPD is this. If that, the FPD is literally those two arrows, and I don't mean just exactly those two arrows, one pointing straight down and one pointing off on an angle up to the left. Is that okay? Okay. No problem. No problem. Could you pronounce your, I'm sorry though, I hate to do this and you could still stay quiet, but I just feel like I'm always saying your name wrong. Could you say your name once?
You're always right. My name is Hyun Jong Kim.
Oh, I am right. Oh, okay. Well, good. Oh, thanks. And I won't make you talk again, but man, I appreciate how early you always are to class and everything. Okay, great. Okay. So any other, is everybody else good? Then I will go. If we're all good. Okay, goodbye.